All smooths have a method. All of them have a time scale. For a filter, for instance, that's usually the width of the filter. A long time scale, that is to say, associated with wide filters, they're slow smooths. They change slowly, and short time scale smooths are fast smooths. Slow smooths will wipe out fast signal, so we may actually eradicate some signal if our smooth is too slow. On the other hand, it will at least reveal to us what the slow part of the signal is. The smooths tend to identify the slow stuff as signal and the fast stuff as noise. This is not often the case, but it's not always the case. Just like model fits, they usually will fit the signal, mainly at least we hope, but they'll also fit part of the noise. Let's face it, smoothing method, filter, whatever, put noise in, you're going to get some noise out. With luck, most of what you see come out of your smoothing method will reflect signal, but some of it will be due to noise. So even if the signal is perfectly smooth, the smoothed estimate might be kind of wiggly and irregular. Let's take a look at some real data. No more of the artificial data stuff. Let's look at global temperature, monthly averages for the entire planet Earth, actually global temperature anomaly, according to NASA. Here are annual averages from May through April, but I want to focus on monthly data. They look like this. Here I've fit a straight line. After all, that's not an uncommon thing to do. First, let's see if there's a real genuine trend. Now, there is a real genuine trend. I tested it according to the usual method, and it came up strongly significant. But that significance is partly at least false. We'll see a good bit about why that is later. I can try higher order polynomials. Here are the residuals, which visually suggest there's more going on than just a straight line. If I fit a quadratic, I get a pretty good fit. There are the residuals from the quadratic. It looks like there might still be more going on. I can try polynomials. Here I tried polynomials from degrees 1 through 12. There's a few things to notice. One is that as the degree gets higher, they tend to converge to what the true signal is in the middle, far from the edges. Although that's just a best guess. Once again, these are real data. We don't know ahead of time what the true signal is. Something we do notice is that at the edges, the higher degree polynomials tend to wiggle far more. That's because the uncertainty and the wiggling around of polynomial filters get bigger and bigger, of polynomial fits, get bigger and bigger as you get closer to the edge of the data. So this stuff where we're seeing a rise in the middle and then some leveling off and then a steep rise, that I trust. But this wiggling stuff at the end, I don't really trust that because I am well aware from much experience of the fact that high-order polynomials can wiggle around too much at the edges of the data. If I used the strategy of fitting higher-order polynomials and taking the p-value for the new estimated term at each step, I would find that for all polynomial degrees from 1 to 12, I'm getting a statistically significant term. That would seem that I need to use that 12th order polynomial. Well, the 12th order polynomial might be good, except at the edges. It still can't be trusted, but it's still useful because it's getting better and better in the middle. However, I don't trust these p-values as being accurate, mainly because of something we're going to see soon. If I use the Akaike information criterion, I see that the AIC gets lower and lower as the polynomial degree gets higher and higher, which indicates that the higher polynomial degree models are better. Possibly they are. In fact, they probably are in the middle, but once again, the fact that they wiggle so much at the edges makes them untrustworthy at the endpoints of the data. That can be especially problematic in cases where we're trying to figure out what's happening recently and what might be happening in times to come, because that depends on a good idea of what the signal is at the edges of the data, and that's something that polynomial fits do especially poorly. The reason I don't really trust the AIC values or the p-values for the polynomial fits is that these data show autocorrelation. I took the residuals from the 12th order polynomial fit and computed the autocorrelation function. There are lots of autocorrelation values that are definitely not 0. At lags up to as high as 13, 14, and even beyond if you really want to get technical about it. So this is a case where the data are some signal plus noise, which is not white noise. That means that the p-values we got out of a computer program that assumes white noise aren't right. The Akaike information criterion estimates that we got out of a computer program that assumes white noise aren't right either. We can apply some smooths. For instance, here is a simple moving average filter, a boxcar filter, on a 1-year time scale. You can see it wiggles around less than the monthly data, but it still wiggles around quite a bit. If I kick that up to a 20-year time scale, I'll get a very nice smooth estimate, but I might have over-smoothed. There might be some things signal-wise happening on timescales less than 20 years that I'm wiping out by a filter that's that wide. Also, I lose 10 years at the edges of the data at the beginning and at the end. I can go with a tint filter instead. On a 1-year time scale, it looks very much like the boxcar filter. On a 20-year time scale, it looks very much like the boxcar filter, although it's a bit less wiggly. There are fewer small little micro wiggles around. I can go with a Gaussian smooth. On a fast time scale, I'm still getting wiggles, but if I go to a longer time scale, I'm going to get a nicer estimate of what the actual values are, and I can push it to the edges of the data. Problem with Gaussian filters, though, is that you can't really trust the very edges of the data because there are edge effects with a Gaussian filter, especially when there's a trend at the end. In particular, there's a rising trend at the end of the data, and a Gaussian filter will tend to mute that rising trend and make it look like the trend is leveling off, when in fact the data happen to be going up dramatically at the very end of the data. If I use my favorite, the low S smooth, on a short time scale, it looks like all the others on a short time scale. On a longer time scale, it is perhaps the most reliable of the smoothing methods I've applied so far. We can see that we may have eradicated some signal because the sum of the signal, in particular here in the 1940s, is happening on a faster time scale than my filter or my smoothing method allows for. But what we do get that's reliable out of this is that there has been a steady rise since around the 1970s, and it hasn't slowed down. It did not level off, whereas the Gaussian filter made it look like it did level off because of edge effects with the Gaussian filter. The low S smooth doesn't have those particular edge effects, nor does it accelerate upward too much because this is my modified low S smooth, which is designed to eliminate too much curvature at the endpoints of time. I've got a little project for you. I want you to find some data, some real-world data, not artificial data. Find the software that you want to do time series analysis or just analysis in general. Do some averages, not moving averages, but just plain averages. Plot them and make some graphs. Do some moving averages. Do a Gaussian smooth. Do a low S smooth. If you can program a bit, create some program to do your own tint filter. Go exploring through the data. Try polynomial fits. Be aware of edge effects there. Try the smooths. Play around with them a lot. Experience really counts in time series analysis. Even if you learn all the theory and ace the tests, there's still a lot to be learned from experience. There are mistakes you will make. There are tricky situations you'll encounter, and you won't really know about them until you make the mistakes and encounter the tricky situations they trick you. But through the experience of getting fooled and making mistakes, you'll learn how not to get fooled and make mistakes in the future. The more you use the available tools, the more you will understand them, their properties, their useful characteristics, their caveats. Do it until you're blue in the face. When you are at the place where you've done it so much that you really are starting to see it when you close your eyes to go to sleep at night, that's when you have begun to get good at it. By the way, hold on to this data and hold on to the results you get from looking at it. Because before too very long, we're going to work with that same data again, at least I'd like you to. One of the things we're going to do very soon is get into how to compute the uncertainties associated with all the smooths that we have outlined so far.